Hey, this is Paul Soltz, and we're going to make a LRU cache. That's a least recently used cache, and we're going to do it in Swift, and we're going to try and do it quickly. So this first time I tried it, it took 4 hours, and then I was stuck. The second time I tried it, it took another 4 hours. Then I got a solution, but I realized that I needed to work on my linked lists. So then I spent time doing that. I was able to get it in like 1 hour in like 2 minutes. And that was better, but it still needs to be faster. So then I worked more on my linked lists and just getting an understanding of that, being able to draw them really quick. So we're going to see how fast we can do it. I'm hoping I can do it in half an hour or less. And we're going to go ahead and get started. This is going to cover generics. It's going to cover protocol conformance and associated types. So that adds a little bit of complexity to the code. And I'm going to try and approach it differently. So in the past, I was trying to get a working implementation of the cache and then enhancing it. The problem with that is that you have to repeat and revisit code. And I think that's a mistake. So as much as possible, I'm trying not to revisit code that I've already written. And the goal is assume I can write the linked list perfectly, that there are no errors. Assuming that it compiles, it should be pretty correct. Then we'll write the algorithm on top of that. If I need to, I can implement the print. Print will add about 3 minutes to get debug printing. So I know it's gonna have cost. So I'm going to, can't write. I'm going to punt printing until I absolutely need it, because there are unit tests that will tell me if I'm passing or failing. And so the point of this exercise is to see if I can write it as quickly as possible. And then I'm going to try it again in a coder pad where I'm going to have a very limited pass-fail unit test that's going to just tell me if it's working or not. And I think this is probably going to be half an hour, but I know that the links, so for me to do the linked list, that takes 6 minutes. I would say 6 to 9 minutes if I'm doing debugging. And that doesn't leave a whole lot of time. So so the way this is going to work is, let's explain the problem. I'll propose a solution and and then we're going to just code it up. I'm not going to draw all the edge cases. I'm just going to have a couple diagrams that are going to help me think about it, and then I'm going to code. And I think that's going to be the most effective tactic, because you really don't have time to think about this. You don't have time to debug. You just have to do it. And that's the hardest thing about these challenges, is you've really got to focus it. There's going to be some edge cases that I think you just ignore because you can't make it work for everything and test it in a reasonable amount of time. I can't have confidence that I'm hitting all the tests for the edge cases of the first node is getting deleted or the last node is getting deleted. And that's why I've written a perfect linked list that I'm sort of memorizing, so that it's easier for me to just crank out some code and have confidence in it without second guessing that portion of the code challenge as we get started. Okay, so first is explain, then propose, then code. Okay, so let's hit the timer and talk about what we have here. All right, so we're doing a LRU cache, and we've got a key that is hashable so that every item has a key that is a key type, and that allows us to pass in it. Then we have a cache that's going to have an associated item that is a cache item, so that we know that every item has a key. The size is an int, and the size is the max size. Then we're going to have a read function that takes in a key that is the item's key from a cache item. And then we've got and it returns us an item if it exists. Otherwise, it's optional. Then we've got a write function that is going to write into the cache. Now, the things that we need to keep in mind is that a read and a write, I would say both of these are going to be cache hits, which means that we need to mark as most recent. Okay, and then we've got string conforming to this as well as int. I think in this example, we have some tests. Now, the tests, these were provided. I just converted them to XC test for this example. If I'm doing an encoder pad, I would have the pass-fail tests that were given to me because you won't be able to run XC test. So we're expecting that if we write 3 elements and then we read those 3 elements, they're all marked and they're all getting updated as most recent. We're writing a new element. It's going to get rid of the last used, which would have been this element right here if the max size is 3. Then if we read 2, we see that it's nil. Then we try and read these in a certain order so that we get into this ordering. We read one more time 3 to get a cache hit. Then we write 7, so we add an element so that 4, which was this element, gets removed. And then we verify that that is nil. And then we do another read just to verify that things are what we expect. Okay, so there's a couple tests in here. That's the gist of it. So let's dive in. And what do we need to do? So I want this to be, so anytime we're doing caching, we're going to use a dictionary. So the building block is going to be a dictionary of some type. And that's going to be typed to the keys. So item.key. And then we're going to have some kind of value. So you're going to have your item here. And that's going to give us a quick lookup so that we can get to that item quickly. The problem is we also need to keep track of the most recent. And so this will give us O of 1 insert as well as O of 1, let's say get. The problem is we also need to keep track of the most recent, and we could do that with some kind of metadata like a date, but then we have to loop through. So if I used a date, we'd loop through O of n times in order to find the date, and that's no good. So what we could do is use a doubly linked list. So doubly linked list. And that's going to look something like this. And let's say we have some values. There's going to be a back pointer on these. Okay, and then if we do some coloring, we're going to have a head. We're going to have a tail. This is going to be our next. Next. I'm going to use prev for previous just to be a little bit more concise because we have limited time and I don't have all the time in the world to type this code. Okay, so that's going to be our doubly linked list. And then as we see things, one of the things that we're going to need to do, and I should have probably given myself a little bit more space. So if I want to retrieve something, if I'm saying, let's say we go back to my pen tool, we're going to say dictionary at 7. And so we're doing a cache hit. And so we've got to return 7, but we also have to mark it as most recent. So and maybe I should, I'm jumping the gun a little bit. Let's just say this is a read 7. So that's our key. So we need to use our dictionary to get the thing associated with 7, and then mark as most recent. And so what we can do is we can say, okay, well, let's consider this side is most recent, and then this side is least recent. And when we do this read, what we're going to do is we're just going to remove an element. So let's switch to red. So we're going to say, get rid of this. And then we've got to adjust these pointers. Oops, that's next. And then we've got to insert. So this is going to be step 1, delete, and then we want to insert. So 2, 1 goes here. These all go away. This goes away. This is 2, and then 2 is going to point up here to nil. And we're going to have back reference as well. Okay, so that's kind of our starting point. One moment, someone's at the door, so we're going to have to pause. Okay, so continuing on, I realize this is a little confusing. This is our first step, and then our second step. I don't know why I put 2 here. This should be 7. This is our second step. Okay, so that's just the read. The write's going to be similar. We're just going to append to the end. So and then the other thing I need to update the count. So those are our 2 things. I think that's enough to go on. The dictionary is basically going to be pointing to these nodes so that we can get those quick lookups. So anytime we add them, instead of up here, we talked about having this be item, we're instead going to do a node to an item. Okay, so let's jump into code. That's 10 minutes. I don't want to spend any more time on that because this is going to take some time to implement. And I have a Frisbee game tonight that I want to get to on time. So I'm going to have like a 20-minute cutoff. So we'll see if we can do that. A lot of timers going on right now. All right, so the first thing that I'm going to do is I'm going to implement this doubly linked list so that we have a data structure that we can work with. And then we'll implement the algorithm. Okay, so I'm going to try and do it top down as I go. So we're going to start with the node class. And the node is going to have next, previous, and item. These are going to be optional types. Actually, we could be using this lap timer, so let's just hit that so we keep track of our laps. Just move this up. I need to make this equatable. I may make it printable later on if we have problems, but I'm going to start off not doing that. Doing everything assuming I don't have code completion, so just writing it out. And I can adjust this later depending on the write-up of the description, or like asking questions of like, how should I be comparing things? Right now I'm just comparing pointers, but if I was guaranteed unique items, I might change how that works. So that's our initial approach for the node. Let's go ahead and make our linked list. Everything here is written to be abbreviated a little bit, so I'm not going to call it doubly linked list. I'm just going to call it linked list. The linked list is going to have a head, a tail, and a count. I'm going to assign this to 0 so I don't have to write an initializer, and then we're going to have a function append. And then we're going to have a function delete. Now, I'd ideally want to write tests for all of this, but I don't have time to do that. So I'm going to try and write this so that there are no bugs. So if we're appending and the head is nil, we're going to have a base case here. So if head is equal to nil, then we know that we need to insert our first node. So then head is equal to node, and then we're kind of done there. Else, we're going to need to do something else, and then we're going to keep track of the count. So count plus equals 1. We're going to add every time we add, no matter where. And then the other thing is we're always appending to tail. So tail is always equal to this node once it is inserted. Next, we need to insert the node. And so to do that, if it's not the head, we're always appending onto the tail. So tail dot next is going to equal our new node. Tail is an optional type, so we need to use the optional chaining. And then we're going to say we're going to say node dot next is equal to nil. And we also have a previous reference that we have to set. So let's go ahead and set that. Node dot previous is equal to our current tail before we update the tail. And so that should be pretty good for our append. And then for our deletion, let's move this up. For deleting, what do we need to do? We're going to update our pointers. Okay, so we're going to say, and this is where we have to think about these pointers. So whatever 7's previous next needs to be updated. So so we're going to say node.previous.next is going to equal whatever our node's next was. And then our node's next dot previous, so we're going in the reverse direction from 7 next previous, so 1's got to point to 4, so previous is equal to node dot previous. And then we have two base cases where we have to do some accounting for the head and the tail. So if head is equal to node, then we need to say head is equal to head dot next. And the other edge case is if the tail is equal to the node, we need to say tail is equal to tail dot previous. And then we need to update our count. So count minus equals 1. Now this is assuming that the node that we're deleting is always getting deleted. And I'm doing this because I need a reference to the node in order to remove it for this one. Okay, so we can go ahead and build and nothing is going to happen, but that's our basic logic. So next up, we need to get into what we're trying to do when we read. So we need our dictionary and we need our linked list. So let's go ahead and make our dictionary. This is going to be of type item.key to node of item. And then we're going to have a list of items. And I think that's it. I'm just going to initialize both of these here just to, I think, save on time. Okay, so then if we want to read, what do we need to do? Let's try and write this a different way. Guard let item is equal to our dictionary at the key, else return nil. And then, so that should cover those two things. And then we need to make it most recent. So to do that, we're going to say list dot delete this. Oh, it's not an item. We're doing nodes now. So list dot delete node. And then list dot append node. Okay. So that's going to be read. And oh, I didn't mark the time. Let's do another lap. How long that took. Okay. So I've got 10 minutes. To write, what do we need to do? Writing is we're appending it and then we're managing the count. Oh, we forgot to manage. Do we delete? Yes, we're doing counts down at the bottom. Great. So writing it, we need to see if the item exists. Potentially we want to update it. And then mark as most recent, and then append. So how can we write this? If let node equals dictionary.key node.item equals item. That's how we're going to update it. And then we have to mark it as recent. But I think we're going to do that in all cases. So are we? I think we have to mark it as recent here because here, okay, so then we'll do the same thing we did up top. We delete the node and list append the node. And then otherwise, what is our else condition here? So we want to append it. So list.append node and then dictionary at item.key is equal to, and then in this case, we have to create a new node with an item. So item, and we pass that in. And what node are we appending? Well, this is the node we need right here. So if we do that and we go ahead and run, what is wrong here? Oh, and you know what else we forgot is the eviction. So we didn't even talk about that. I skipped right over that. There's a max size here. Okay, so we're gonna remove it from the head if that's true. Okay, so let's go ahead and implement this before we dig too deep into those unit tests. So what we need to say here is if the list.count is greater than or equal to size, then we want to pull off stuff from the front. So if we look at the notes, this is where we're always going to remove from. This is our least recent. So 4, if we were hitting our limit, would be the first thing to get rid of. So let's get the head. So we'll get a reference to the head if we're over the size, and that's potentially an optional value, but we don't use optional chaining to get to it. This is always tripping me up. So then in here, what we need to do is set so we have to remove from dictionary and list. So we're going to say dictionary at item, sorry, at head.key, you have to be really careful here. You could like trash everything, is going to equal nil. And that's going to be head.item.key is equal to nil. That'll clear it out of the dictionary. And then we want to say list.delete. And then in this case, head. And all of our unit tests succeeded. So we just finished this. It took me 26 minutes and 2 seconds to write this. I had a little bit of a, this is like the fastest I've ever done it. I don't know if my explanations were great. But that is my solution for this code challenge. So hopefully you find this to be helpful. We can go look at the unit tests that passed. We can see a bunch of green here. Just checking some of the reads, some of the writes. The main thing was just verifying that the elements could be removed. Now, the tests weren't super exhaustive for this, so I'm not expecting like perfect code in all situations, but I think this hits on a lot of the things that we need. So just to summarize what we're doing here, when we're reading the key, now this is what I deviated from what I've done in the past, is I just decided to use the guard let and return nil if we're not finding it. And then that made this easier, so I had less optionals. So that took away some of the optional chaining, which I think I would have to do, or I'd have to do an if let. I think I did an if let before. So I thought that was a little bit nicer to look at, a little bit less optional chaining. And then for the write, this is where I kind of I just couldn't remember what I was supposed to do here or what I was doing. And I should have written out some of these steps or like gone back to be like, okay, what are we doing? And I think we didn't spend as much time. We spent a lot more time on the read. So that was top of mind, but the writes I kind of glossed over. So I kind of struggled with that. So what did we learn from this? The initial talk time was 11 minutes. I had something somewhat functional with the linked list by, I think, 6 to 8 minutes. And then it was another, oh, did I hit the wrong button? It was another 6 minutes to implement the actual algorithm, which is actually interesting. Significantly faster from preparing this. And I did not do any kind of printing. So if we want to actually see if like how these things are looking, let's just go in and do that real quick. Most likely, that I'm kind of skipping a step. I didn't actually try and like walk through this with any examples. And so that's probably something that you'll want to do if you have the time. Like now I have time. I didn't have time before. So I could actually step through the examples, talk about what it's doing, and run through that, which I might use the iPad to do since I have to run out the door to a Frisbee game. I'm not going to do that right now, but that's something that we could do. I don't even have time to do the custom string convertible. So we're just going to trust that it works because our unit test passed. And actually, I don't know if I have any, did I get rid of all the print statements? Yeah, I got rid of all the print statements. So this is just asserts. So if you are stuck debugging, now you have a problem. And so that's why I think practicing this a couple times has been super helpful for me. I've maybe over-indexed on this a little bit, but I think being comfortable making a linked list from scratch and knowing that my edge cases are pretty solid, like this felt solid. I didn't know exactly where I was going here. And that's where the unit test could sort of help you be like, oh, I forgot we're evicting stuff. So I might be a little bit more verbose on like, what is the algorithm? Let's think about the algorithm first before we jump into code, because I didn't spend enough time on that. I spent a lot more time on the linked list, maybe too much. And I think, I think I would I've got to think about how I would describe this problem a little bit better, because I sort of knew the trick. And if you don't know the trick, this problem's really hard, which is that you have to use both a dictionary and a list, and that you've got to have a doubly linked list, and you've got to store references to nodes so that you have O of 0. So if we're looking at this, this is going to be O of 0, no, so O of 1 lookup times. That's really important. And then this is going to give us O of 1. So constant time removal of least recent node or value item. So that's why we need the two, and they work together. All right, thanks for watching. I hope this was useful. We've got a bunch of timers here. Try this yourself. I've got a starter project that you can use, and then I'll have this code that you can look at, as well as a solution code. All of that is going to be together in the download. So it's going to look something like this. This is my 5th attempt outside. So the first attempt was at the interview, and I'd seen this before 2 years, 3, 4 years ago. And I still struggled with it. Like, this attempt took 4 hours. This attempt took 4 hours, but got me to solution code. This attempt took 1 hour. And this attempt now took, we said 26 minutes and 2 seconds. All right. So I guess it is possible if you understand some of the fundamental structures and can think clearly. It's still a struggle. I'd probably want to do this again and talk through it again just to feel confident I'm actually explaining, because I don't think I explained it well before diving into the code. All right. Thanks for watching. Click the like button if this was helpful, and I'll see you in the next video.